So, welcome everyone to episode 2 of the Math-a-thon. I really need to learn how to say that word, which is not a word, but anyways. So, right now I'm studying for a real analysis thing, which is why you're seeing a bunch of, just practice exercises. Today we're going to be covering limits, and I'm saying we as if I'm going to be teaching this, but truthfully I'm reviewing as well, and some of these concepts are not necessarily fresh in my head or like how I will solve these issues. So it's really just me recording myself as I go through. And yeah, hopefully that can serve as content. So that intro is already way too long, so I'll just get going. I got a timer. So I'll be going for 90-minute sprints. Just for as long as I can, and then when it's no longer productive, then I'm just gonna stop. So let's get started. Limits. So suppose an is a sequence of real numbers and r is some natural number. Then the sequence an converges if and only if the sequence an plus r converges. Okay, so if we can essentially kind of jump ahead in the sequence by r, and this converges, then an converges and vice versa. This makes a lot of sense. Like, it just means that if I have some sequence and this goes to infinity, well, it doesn't matter if I start at this point, like if I start from here, which is a proper start, or if I start caring about it at this point. If this thing here diverges, and this diverges, and vice versa. So now, how do we show that? If these sequences converges, then limit of an is equal to an plus r. Well, yes, that has to be true as well, because like they are the same thing pretty much. But how do you show that? Okay. This is a proposition. Which part are we asked to prove? Suppose an is a sequence of real numbers and r is a natural number. Then sequence an converges if and only if the sequence. Okay. If these sequences converges, then that. Okay, so we have to prove this, I guess. And then that, I suppose. Okay, sure. So let's try to think through that. Well, what does it mean for an to converge, right? An converges if for any epsilon, I write e as epsilon because I still haven't fixed my MathJax issue. If for any epsilon greater than 0, okay, there exists some n such that for any n greater than or equal to that first n we chose, I need a concept of a limit. Yeah, I need a concept of a limit it's going to be converging to some. Right now, what I'm saying might not be making sense, but there's two ways typically to approach these kind of problems. If I'm saying that a sequence converges, then it means that the sequence has a limit. And so if I'm able to show that a sequence if I'm able to show that some sequence has a limit, then I've shown that it converges. But there are times that I'm not really sure what a sequence is, and so I approach that using the Cauchy sequence definition, because a Cauchy sequence, if a sequence is Cauchy, then it's also, a convergent sequence. Okay, they're equivalent. And so in the Cauchy case, then I would have a n. I would have I would have this here. What would happen is that I would have some n, such that for any n m, the absolute value between the absolute difference, well, the distance between those two is less than epsilon for anything beyond. I don't know if it makes sense to use that in this context, but since there's no specific limit to speak of, it might make sense. Yeah, because right now we're just trying to show that an converges if and only if an plus r converges. So since we have an if and only if statement, it probably makes sense to approach it just try to show the directions we have to show. P then Q is essentially the idea that okay, the timer's running, so I'm just gonna close that so that I'm not bothered. Let me put that on do not disturb. Yeah. Okay. So for the first way, what I'm saying is n converges if an converges, an plus r converges. Okay. The other way is if an plus r converges, an converges. Okay. Well, I can use the Cauchy sequence definition. Okay, since I don't have any limit to speak of here. And say if an converges, then for any epsilon greater than 0, there exists n such that, and like I know that I have it written above, but a thing that I tend to do when working on math problems like this is just always type the definition, because then at some point the definition is just like anchored in my brain, so I don't even need to think about it too much. And so if an converges, then for any dot we have an minus am okay, I can do a nice less than epsilon. Okay, and so if we have that for an converges, well, logically, then an plus, therefore, for any m plus r n plus r greater than or equal to n, we have, I think that's all I need to show, no? N plus r therefore also a Cauchy sequence, and therefore convergent. I think that works. I don't see why that wouldn't work. So I'll keep going with this idea, because if we can use the Cauchy sequence definition, then if n plus r converges, it's a little bit less convenient, because now okay, what changes here? Since convergent is about a tail behavior anyways, advancing by r doesn't really change a thing. But How do I express that mathematically? Like we know that that n plus r converges. Okay. Okay. So by the Cauchy criterion, okay, for all epsilon greater than 0, we have some n such that um such that n, okay, n, let's call that n prime, which is defined by n to be equal to n plus r, and n prime which is equal to be, which is defined to be m plus r, okay, greater than n, we have the absolute value. Oh wow, I'm already there. I'll make this a tiny bit smaller. Keep going. Is it recording? Yes, it is. So, boom. Let's move that here. Okay. So now we have n prime minus a n prime, and that has to be less than epsilon. So what kind of manipulation I can do, to still get my convergence of the original sequence? I mean, I'm not too sure actually. I could think of the idea of a bijection between the two sets, but I'm not really sure that it helps in the sense of, like, to show that the convergence thing that I want to show. An plus r converges. An converges. This much, like, it just makes sense. But how do I express that? An plus r converges. What does that tell me? That tells me what I wrote. And so how can I express that as? Wait, isn't that sufficient? Yeah, wait. Isn't that sufficient, what I just wrote? Yeah. Okay. Yeah, I think that's sufficient. Wait, someone sent me a message. I should mute that as well. But yeah, I think that might be sufficient. Because, like, right now, I was trying to, like, find a clever way to express this idea. But I don't even need to do that because, fundamentally, what we have here are terms of the original sequence. So, n plus r, if this converges, okay, note that all terms n prime m prime greater than n are terms of an as well. Therefore, I think I'm allowed to do that. Therefore, trivially, the Cauchy criterion holds for if someone could double check me on that, but I think it works. Okay, so that's good. I'm gonna squish that because now the second thing I want to show, right now I showed that if one converges, the other converges as well. Okay, but what is the interesting thing is actually that part here. They have the same limit, which, well, yet again, it makes perfect sense because, like, if this converges to something, this one is just like a few steps ahead of this one, so this one is going to be lagging behind, but it's going to be approaching the same thing. So that's an obvious idea, let's say, maybe. But how do I show that? Okay. Well, we already showed part of the work, and maybe it would have made sense to like just do that from the start, but anyways, it doesn't matter at this point. So we showed that an converges if a n plus 1 plus r converges. Now we want to show they converge to the same thing. Okay. Let's see if we can have a sketch of this. So we have this here, which is our sequence, and we claim that this converges to some L1. Okay, and we have this part here, and we somehow we want that to converge to some L2. Okay. Okay. Well, no, actually. I mean, that's the assumption that is, like, the assumption is that this is impossible. Okay? And so it would make sense to tackle this as a contradiction. Okay? Show that, okay, we are saying that. But the thing is, here, this is so obviously not true that, like, the sketch doesn't really reveal anything. Yeah. So I would want to show that. Yeah, okay, I'm not really too sure how to formulate that at this point. So let's just try to see. Let's just like grope around and like see if we find something. Converge towards the same thing. For the sake of a contradiction, we claim the opposite. Okay, let's just start with that and let's see where that takes us. So, let lim an equal L1 and lim an plus r equal L2. By definition of limit for both of them, okay, there is some n, and here we're gonna have a general n, like, let's call that max of n1 and 2, such that for all n's, and let's say n1 and n2 greater than n, we have an minus L1 is less than epsilon, and I guess, and here I'm using coding and mathematics. Yeah, we'll have that here, and 2. Okay, that's not supposed to be 2 here, like that. Okay. Well, the obvious thing is that this one is lagging behind, so at some point, this here would become that. Okay. But how do I show that? I'm not too sure. Well, one thing I can start with is that every n2 is of the form n plus some r, right? Is of the form n plus some r. Okay, so I can rewrite that. As a n plus r minus L2 less than E. Okay. Okay. Well, intuitively, if I take n1 and then I add plus r, then it becomes some term of the second sequence. But I'm not too sure that it shows what I want. Ah, frick, how do I show that? Well, from the absolute value, I can rewrite it as this n plus r minus L2 epsilon. Okay. And then do okay, let's do, I don't know where it's gonna take me. Okay. So let's just do algebra on this, okay? And we'll do a similar thing with the other one where we have L1 minus epsilon less than En less than L1 plus, why do I keep writing 2 epsilon here? Okay. So if I add both of them, let's say I subtract an from this. I don't know where I'm trying to get. Maybe I don't know where I'm trying to get with this, but we'll see. So if I do an plus r minus an here, okay. Well, I remove the big. Okay, this is less than this. I remove this from it. Do I have a theorem on the relation on these? I'm not even sure I can maintain the inequality. Because if I do an plus r minus an, and I do L2e minus L1e, what happens now is that I cancel that e, which is nice. But then which side goes the equality? Well, is it even nice? No, actually, it's not really nice, because then I lose my bounding. But yeah, so frick. Oh wait. Actually, no. Actually, it's kind of nice, because then I have this, which is between L1, L2 minus L1, and L1 minus L2. Would that tell me that they're the same? Maybe. That might be an idea, but right now I'm really just like voicing my thoughts. I don't know if I'm going where that's gonna lead me. I don't think that's necessarily true. Wait, let me try to find an example, a counterexample. So let's say I put that here and have 2, 3, and I have, yeah, it definitely doesn't. Let's say I have 10, 11. 2 minus, that's gonna be giving me minus 8. This is gonna give me minus 8 as well. Wait, no, it won't give me minus 8. Yes, it will. It will give me minus 8. So now we have equality. Yes. So I can't maintain the relationship necessarily. Now we have equality. Well, that's annoying. Yeah, that's annoying. So this is not what I need. Okay. I mean, wait, wait, wait. Do I need? Can't. Yeah. Wait. Isn't it really simple? Can't I just do an? We claim an converges. Therefore, L exists such that for all greater than 0, an minus L. Can't I just do this? There exists and such that that right and I do let n be greater than n plus n, then n plus r such that an plus r in sequence an plus r. Okay. Then for all n greater than do such that and and we have a n plus r minus l as an epsilon for all epsilon greater than 0. Since L is the same, we conclude that both sequences converge to the same thing. Is that sufficient? Shown? I think fundamentally this makes sense. Like the idea is just that the two, like this one here is this here is kind of like a lagged version, or no, rather this one is a version like looked in the future version of whatever this is, which means that whatever term that appears here will appear in this one as well. Okay, at some point. And so this one has to converge to the same thing. That's obvious. And then an here, all we're doing, I need to mute my Discord. Wait, yeah, let me just mute that. Why won't it let me mute it? Okay, mute low level IQ. Let's mute it for 24 hours. That's fine. Okay. So let's get back to this. So here, what I did is legal because if n is greater than n, then n plus r is surely greater than n as well, and n plus r is part of this sequence, and then all the terms an plus r will be converging to the same, will be like valid for this expression here. So they have to converge to the same thing. And so yeah, I think yeah, if anyone tells me I'm wrong, I'm gonna fight them. Okay. So now we have a case where we have to show that a sequence is divergent. Well, okay, cool. How do we do that? Well, here we're saying that the sequence is divergent and it's divergent to negative infinity. So what does that mean? It means that for any m, okay, here this m stands for like, I don't know, like some minimum, I guess. For any m Okay. There exists a n such that for any n greater than m, the terms of the sequence here, for any terms, okay, will be less than m. So you can never find like a lower bound for it. I think that's, I'm pretty sure that's the definition. Okay, let me just check to make sure. No, I'm gonna trust my gut on this one. So, yeah, like it's not a matter of like trusting your gut. It's just like I can't be bothered to open the textbook. So I'm pretty sure this is the definition. And so, oh, my back. Okay, and so well, this looks to be the case because well, n squared on the bottom we have a difference of squares, so we could write it as n. Yeah, I guess the approach I would take to that is, well, I don't need to simplify it, but if I can simplify it, and like it feels like something that could be simplified, that's what I'm thinking. Yeah, I guess we just need to find some n. Yeah, here the trick is to find I haven't done many problems of this kind where like you have to show that you diverge to infinity or negative infinity, so it's a good thing that I'm seeing it here. What is the next? Okay, cool. Okay, so what do I do here? Well, this is true. So I guess the way I would approach that is I put a m there, and then I try to find some definition of n that will allow me to do that. So I guess I will find n. Okay, I will solve this in terms of m, I guess. In terms of n, I guess that's the way I'm gonna approach that. So, so n cubed minus 3n over n squared minus 1. Well, in this case here, the top, I'm not seeing an obvious way to solve it currently, but we can keep it as is because I have a gut feeling, which might be entirely wrong, but that we can simplify it by just dividing by one of these here, and plus 1. Okay. Just using the difference of squares. Okay. And then what can I do with that? Well, let's see. Can I divide? N would fit. Okay, let's try to do long division on this. Okay, so with I don't know which would make most sense here. I guess my gut would be this one, but I'm not sure. So let's do it. I'm using the mouse right now, so if the writing looks off, sorry. So n plus 1. So n, for us to cancel it in this context, we'll need n squared. Okay, so I do minus, and then I do, wait, I want minus n squared, do I? Yeah, I want minus n squared. Yes. So with minus n squared here, I'm gonna have minus plus, and then it's gonna become plus negative, then it works out. So I'm gonna have n cubed, negative n cubed minus n squared. Okay. This will cancel with this, and then this will become positive. And so now I have n squared minus 3n, and hopefully it divides cleanly, because then I just did it wrong. No, I just want n here. Okay, so I'm gonna have n squared, then I'm gonna have minus n, and you can see it that there's gonna be a leftover here. So I'm gonna have 2n, and then I have no way to cleanly split that. What if I use the other one? If I use n minus 1? Yeah, right now there's no way to cleanly do it. This should go here, by the way. Plus n, and now I have 2n, and I cannot work with that with what I have left, so that doesn't work. How do I erase that? Okay. Oh shoot. Okay, let me do this. Hopefully the other one works, because then, well, I'm not out of ideas, but it just means we kind of wasted time here. Well, no, we didn't waste time. We explored ideas. That's what we did. So n minus 1. Okay. Here to cancel that, same thing. So n squared, I'm going to need that, and I'm going to need it to be negative, so that when I do this, it works out. So this becomes positive, plus n squared. And so this is cancelled still. And I have minus n squared here, minus 3n. To cancel it, I'll have the same problem, no? Sheesh. Okay, so there's none that seems to give me a clean division. Yeah, I won't get a clean division out of that. So n squared plus n. Yeah, now I got minus 4n. Yeah, I can't work at that. So that's not twice. Okay. So maybe I'm overthinking this. Okay, there's probably a simpler way to approach that. Okay. Here I can factor out an n, I guess. If I factor that out, then I'm left with n squared minus 3. And I guess I can even factor out the negative 1. So now I have n inside plus 3. Okay. And n squared plus 3. What do I do with that? I'm not really sure. Like, right now, fundamentally, all I'm trying to do is show that for any bound m that we put on that, we're going to be able to find a greater term. But using real analysis techniques, okay, I cannot just say the limit of this isn't, like, I cannot just use calculus. Like, that's obvious, like, that this is true, but I cannot just do that, okay? So, let's start from scratch. Maybe that's not the right way to go. Okay. Let's write on the bottom here. Okay. So, let's just actually put the inequality. Minus 3n. N squared minus 1. Less than m. Okay. Let's say that everything is less than m. Okay. Well, n squared is clearly positive. And for any n greater than 1, like we cannot have, this is not defined for n equal to 1. Okay. So, but for any n strictly greater than 1, this part here is positive. Okay. So that means that I can do, yeah, maybe I'll just use the mouse from now on. So n3 minus 3n like this. is less than m n squared minus 1. Okay. I can take the -1 out. And so now I have n cubed plus 3n. I don't know how helpful that is. Less than n squared minus 1. Okay. Yeah, I'm not seeing it. And that should be easy. Well, easy. I think it should be. Okay, let's just erase all of that. What am I missing? I'm pretty sure I have the right definition. Let me check the definition just to make sure. Divergence. Definition. Real analysis. I'm pretty sure I'm correct, but just to make sure. Divergence sequence proof wiki. Let's see. Okay. Yeah, no, I need a definition though. Divergent. Yes. Wow, brilliant. Okay. This image maybe. For all m greater than 0, there exists n such that n greater than yes. Oh, yeah, I guess this is supposed to be. The only part I was missing is this here. Since we're saying it's like, if it's positive, this. Well, no, actually. If it's positive, then clearly it's gonna be. No, I don't think I even need that. Yeah, overall I have the right definition, it seems. So, okay, so it's not a failure on that side. So now, how do I approach that then? And we have that. This is true. Is there something I'm missing? Minus n cubed minus 3n. Well, really, what we're saying is that minus n cubed minus 3n n minus 1. I had the inequality on the wrong side to start with. Is greater than m, so lower bounded by n. Okay. Well, if I take n squared here, okay, Maybe what I can do is simplify. Yes, I think that might be the way to go. So I can simplify this so that I have things that are clearly true. So here minus n, this is a negative thing, right? So I can rewrite that as minus of the sum here plus 3n, okay, over n, like that. Okay, if I'm able to show that something that is bigger than that gets less than m for any n we pick, then clearly this will get less than m as well. That's the reasoning I'm following right now. So how can I simplify that? We are taking a negative term and we're making it even more the denominator. If I remove n here, this will be smaller. No, that doesn't. This is not what I want. If I remove the 1 here, this will be. No, this is now smaller. No, wait. This is now bigger. Yes, this is now bigger because I'm dividing by a smaller number. So that's a simplification right there. That already helps. Maybe. Okay. Then what can I do? Well, right. This will be strictly like this one here is we have a smaller term on the bottom. Ah, no, that's not what I want. Wait, why is my brain not working right now? We just started. I have 4, for example, and then I have 3. If I keep 4 the same there, and then I have 3 minus 1, I have 4 here. Well, 4/3 is a bigger number actually than 4/4. So no, I don't have this. This doesn't work. So where I should be focusing my efforts right now is on the numerator. Okay. So I want. Okay, I want something here on top that is also simpler to work with. If I remove less, then surely I'll be bigger. Oh yes, I can do that. And 3 minus n is bigger than surely, because I'm removing less from. Frick, the negative is throwing me off. Okay. Yes, this will work because this is less negative than this one. But the thing that is neat with now what we have is that on top we can still do the difference of squares. So we have wait, will I be able to get? No, I don't get a difference of stuff. Frick. Well, if I remove less, then I might as well just not remove anything at all. Okay, this is less negative than this. Okay, and then keeping everything the same on the bottom. Is this simpler? It's starting to be simpler. What can I do? Yeah, my brain. Okay. This here is equal to n plus 1 and minus 1 that we know. But our goal is to solve in terms of n, so it's not really useful to do that. But if I multiply everything, okay, 1 over, I do this here, okay, then on top I'm gonna have minus n, I'm gonna have 1 minus 1 over and then I have m is less than minus n over 1 minus 1 over n. This is true. Well, this is a positive number. Okay, so I can do m 1 minus 1 n squared less than negative n. Okay. And then I guess I can do negative m here. Yeah, this is not working. Why is it not working? Yeah, no. Okay, I think the fundamental idea of making this simpler is good. I just have the wrong approach. So, this here is the first target. Minus n cubed is as big as I can make that term on top. Wait. Wait. No, it's no. I can do. Yeah, if I do minus n, if I do n squared, then it's gonna converge to minus 1, not. So I need to keep n cubed there. Okay, minus n cubed, n squared minus 1 is bigger than what we have. So if I can show that this one diverges to infinity, then since this one is bigger than that, then clearly this one as well. Okay. Can I make something for my denominator here that would make it simple? Well, I can remove more, I guess. If I remove more, like let's say I remove n here, now I have a smaller number on the denominator, but I have a negative thing, so that is yet bigger. Okay, yeah, maybe we can do that. And so now I have n cubed, I have n over n minus 1 here, so that would cancel that. Okay, is that helpful in any way? So now we have negative n squared over n minus 1, and we want to show that m cannot be okay. goal is to solve in terms of n here. So if I set n here, I'm gonna have mn minus. Oh, I can do mn minus m becomes what? Minus n squared like this. I divide, I do minus n squared minus mn, right? So now I need minus m here, and then I can factor out the n, so I get minus n. Well, if I do minus n, then I just have n plus m here. Okay. And then I do n. God damn. What am I missing? Okay, so I'm gonna get m here. Over n plus m. But then we're back to, I need my n, all my n on the same side. Like, I can change inequality like this, because now I get n plus m. And now it's just like a game of cat. Okay. I guess right now I tried for long enough, so I'll just look online. Show divergence to infinity. Let's watch Math's video.
Remember, when we consider an infinite sequence, where typically intervals of our sequence an, which are equal to n over 2, will be greater than 200 over 2, since n is greater than 200, and 200 over 2 is equal to 100. Thus, the values of the sequence will be greater than 100 whenever n is greater than 200. So the point is, you provide me a big number, and I was able to say, after the 200th term in the sequence, all the following terms are greater than 100. And if I can do this with any arbitrarily large m value,
yes.
If little n is greater than big N, then 2 big nth term is less than that.
Yes.
To when we negative, then we'll begin with let m be less than 0.
Okay, yeah, so I have the right idea. I'm just
fixed negative.
Yeah, so okay. So at the very least I'm not stupid. That's good. Okay, so I have the right definition, and in all likelihood I have the right idea as well. So let's be stubborn and try again. N squared minus 1 here. This is gonna be less than me just simplifying to this over n squared plus 1 and minus 1. If I could somehow simplify that so that it's less than something else that is, well, wait a minute. Wait, I can actually do that. Oh my lord, I can do that. Bro, why did it take so long for me to think of that? Bro, n squared, okay, minus 1 is greater than or equal to 1 for all is no, strictly greater than 1 actually. For all n that we care about. For all n greater than 1. Because we cannot allow n to be 1 in this context, else we have a 0 denominator. Right? But then if we have 2, 3, 4, then we have clearly something. So we can just do minus n cubed. Oh, over 1. Okay? And since we are dividing by a smaller number, then clearly this is, well, a bigger. What am I saying? Yo, the negatives throw me off. No, this will be a smaller. It's the other way around. Fuck me. Oh. Okay. Yes, because since it's a negative number. Yeah, since we're dealing with negative numbers, every time I make it smaller, I'm actually making it. Okay. Yes. Okay. Okay, I was working the wrong way, I guess. So, I need this to be bigger than? If I have n squared minus 1 and I change it with a bigger thing, let's say n squared minus n squared minus n is something that is less negative. Yes, that is less negative than the. Okay, yeah, I think I see what's happening. Okay. the negatives, bro. Okay. It took a while, but I think we're starting to get somewhere. So we want to simplify this, and we need to be careful because for the proof to mean anything, we need to find something that is bigger than this. So we have m here, we have our n cubed minus 3n n squared minus 1, and we need to show something on this side and show that since this will be less than m for any m we pick, and this is less than this, then clearly this is less than m for any m we pick. Okay? But the thing is, if it was the positive way, it's really easy because that's just the way you typically think about those things. But for the negative, there's a few adjustments and it gets like tricky, or at least like to my brain it gets tricky. But if I make this small, I actually make this more negative, so it goes that way. So I need to actually make this bigger so that we go that way, and hopefully it's going to give us something that is smaller. Here, if I make this big, yet again it makes us go that way. So I need to make this less negative. So if I put negative n cubed here, this is going to be less negative. Like just with this change alone, we already made the problem arguably simpler in a sense. In the sense that yes, now we have something that I don't know, but like this is I don't know if what I'm saying is making sense, but like this is gonna be less negative than this. Okay? So if we put 1, 1, like we can put 1, let's say 2, 2, 2, 2 here, if I'm making sense, we're gonna have 8, negative 8, minus 6, so negative 14. Okay, and then we're gonna be dividing by the same thing on the bottom, so we don't need to care about that. So we have negative 14 here, which is clearly gonna be less than negative 8. Okay, and so now we are following the right relation. And I think like from now on, I'm just gonna be checking by plugging numbers in to make sure that I'm doing the right changes. Okay, so we have this, and then negative 8 over here. If we say 2, we're gonna have 4 3 8 over 3. Here I would want this to make, I would want to make this bigger in a way that is actually helpful. So ideally I want to get to a simple thing that I can easily show or solve to make it solve for n for. Okay, so negative n cubed n squared minus 1. How long have we been on this problem? God damn. Okay, I don't know how long we've been on this problem, but like I've been recording for like more than an hour at this point. Wow. Yeah. So this is gonna be long, but okay, it's fine. N cubed, n squared. What other simplification can I do? Okay. I could either add something here, but I'm not sure it's gonna be helpful. To the making this smaller thing, I can put negative n cubed and do negative this minus, let's say, n. I know I tried it earlier, but that what it allows me to do is to change that into negative n squared over n minus 1, pretty much. Okay, that's what it allows me to do. And strictly, do I need to do that? Not necessarily, but it makes it maybe simpler to think about. Okay. Then what else can we do? Well, can we solve for this? Is there something else that we can do? Wait. We have a difference of... Okay, let me look up difference of cubes. Is there a way? Maybe the trick is in the difference of cubes. Like, I'm spending a lot of time on this problem because, like, if I can't solve that, I'm kind of cooked. Like, it feels like it's a kind of problem that could really easily fall on a test, and I should have been able to solve that in 10 minutes. So what is happening? Here, if I do 9, for example, okay, I make this numerator bigger, essentially. Well, less negative. Okay. Then what will happen? Here I would have a difference of squares. Then I would have 3 minus n, and then 3 plus 9. Wait, no, it'd be 27, not 3. So 27 minus y here. Then I would have 3 minus n. Then I would have 9 plus 3n plus n squared. And then can I do something with that n squared? Because wait, if we have n squared, I said 3n, right? Plus 3n plus 9. What sums to 2? What sums to 3? But has a product of 9. Yeah, there's no... Yeah. Okay, so that's not the right way to go. What sums to 3 and has a product of 9? Yes, no, that's not the way to go. So, can I solve from this point? If I want, I'm gonna have n minus... No, that's what we did earlier, so no. if I make this smaller, then I no longer have the guarantee. But if I'm able to show that negative n, okay. But then if I have negative n, now maybe I might be able to do something. Because if I have negative n, and I'm able to show that negative n is less than, well, I guess I can just plug a number into that. So 3, negative 2, here I get 2, and here I get negative 14. We did earlier. No, wait, if I put 2 here, I get, yes, negative 14 over 4 minus 1. So 4 minus 1 will be 3, negative 14 over 3. I'm pretty sure that's less negative than negative n. So negative 14 over 3. Oh, whoops. Over 3. Why is it not making over 3? Yes, it's less negative. And, well, at this point, okay, at this point, we can very clearly show that if m is less than negative n, for all n, then it means that negative m is, like, if I put for all n such that for all n such that negative m is greater. Okay, so I set that to be equal to negative m. Okay, and then for all n greater than that, then negative n is less than, well, m, pretty much. Okay, and since negative n is like this here, we have negative 3 cubed minus 3n on top, and squared minus 1, then we are happy. That's the idea of the proof. Okay, and then, so essentially the trick we used is simplify as much as possible, and then do the solving on the simplification. I don't know if that's the standard approach to do it, but that's what I could think of in this context. And then, now that we have that, I guess the only point of contention would be, well, is that actually less than that all the time? And then how would I prove that? I guess, well, how would I prove it? Because right now that's a key element of my proof. But am I allowed to just assume that? Not really. So I could do negative n like that, n squared plus 3. Okay. And I do n squared minus 1. And I guess that's my proof there. Minus n. Okay. Because if I divide both sides by minus n, then now I have 1, which is bigger than n squared plus 3 over n squared minus 1, which, well, that is true. That is clearly true. Right? Yeah. Yeah. But in case, like, I don't need to stop there, because I can just do n squared n squared minus 1 like that. Then I do n squared plus 4 is bigger than n squared, and even I can just cancel it on both sides and get 4 is greater than 0, which is a tautology, so this is true as well. So I think that checks out. So that's how it go. That's how, well, it took way too long, but I think that works. So cool. The negation of, I don't think I need to prove that because that's just what it means. The negation is of for all epsilon greater than 0 there exists n natural such that, yeah, that there exists some epsilon such that for all n, yes, okay. So we're just saying that if we're saying that something converges, then the opposite of that is just that there's like the negation of the statement is just going to be this here, that there exists some epsilon such that no matter how far in the sequence you get, you can never get within the range described by epsilon. And so that means that the sequence is always at least epsilon apart from your limit, and so if that happens, then clearly your limit is not correct. Okay. So just a quick pause to talk with my sis. So if an is a sequence of positive numbers converging to 0, show that square root of n also converges to 0. Okay, so we have a sequence of converging number. Well, at this point, I know of the squeeze theorem, and so I can just do 0 converges to 0, which is less than an, which is greater than an, and an converges to 0. Okay, and so by squeeze, this one converges to 0 as well. Okay, that's just an application of the squeeze theorem, pretty straightforward. But what if I didn't use the squeeze theorem? Okay, what if I didn't know it? Well, what if I didn't know squeeze theorem? Well, if an converges to 0, it means that an, the absolute value of an is less than epsilon for all. Okay, and since an is convergent itself, then we can just literally just write an less than epsilon. Okay. Here I'm like not stating the entire definition. Like it's for all epsilon greater than 0, there exists an n such that this holds. Okay. Okay. And so if this is true, well, an is less than epsilon. Well, an is less than epsilon. Square root of an is less than an, which is less than epsilon, so it's still the same thing. Okay, and square root of an is perfectly equal to this here, which is less than epsilon. Okay, these two are equivalent. And so if we have that, then we have for all epsilon greater than 0, there exists n such that absolute value of square root of an is, well, minus 0, I guess, for the convergence, but I really don't need to say that, is less than epsilon. And then you're done. Therefore, square root of an converges to 0. Huyon, please sponsor me. I need a tablet. Prove that if an converges to infinity, then yeah, well, that sounds fairly well, it's kind of just what we did earlier, no? An converges to infinity, right? If an oh wait, actually no, it's not necessarily what we did earlier. But n converges to infinity, that tells me that for all m greater than 0, there exists n such that for all n greater than or equal to that n, okay, and this symbol is funny. For all n greater than or equal to that n, m is gonna be for converge to infinity. This is the one that is true. Wait. Did I prove the right thing here? M is less. Okay. And here. Okay, yes, okay, phew. For a second, I was like, did I prove the wrong thing? Okay. So, yeah, that's that. And then we know that, well, an squared is always greater than or equal to an. Wait, actually, do we know that? No, we don't. Oops, I almost said something foolish. We don't know that. Yeah, we don't know that because if it was a sequence of numbers going like less than 1, for example, but then it wouldn't converge to infinity. Well, if m is less than an, I don't. Yeah, because 0.5 is less than 0.7. Let me check that. 0.5 is less than 0.7, but I'm not sure that 0.5 squared would be 0.25, and 0.7 squared, it would still be greater than 0.7, no? 0.7 times 0.7. Yeah, it would be bigger. Yeah, so we can't just do it on that side unilaterally, but we can do m squared like this, no? An squared. Okay. Okay. And so for all m that we pick for this, m squared for each m that we pick, an will be bigger than that at some point, and then m squared will be bigger than an squared at some point. I think that works out. Okay. So now suppose, how far ahead? I don't think we're that far. Suppose xn converges to infinity. We'll show that is 1. Okay, that is just a demonstration. Huh? Let epsilon be greater than 0. Choose m in n such that m is less than, such that 1 over epsilon minus. Okay. We can choose n such that, yeah, that's true. And then we have xn plus 1 is equal to minus 1 plus xn. Yeah, sure. Which is equal to 1 over 1 plus xn. Sure. Less than or equal to 1 plus m, since m is less than xn. Yes, sure. Which is equal to epsilon. No, the converse. Yeah. I'm just kind of confused by where did we use the definition. Um, xn minus 1. Oh, it appeared. Okay, it's there. It's there. Okay. So xn minus. Okay. Is equal to that. Yes, it is true. And then that is equal to that, which is less than. Where did epsilon come from? What to find. Okay, we choose m specifically such that it is bigger than that. And so then we can do m plus 1. Oh, that's pretty clever. Oh, that's really clever. Okay. So then we define m specifically such that it's that, such that this inequality holds. So then we can rewrite it as m plus 1 greater than 1 over epsilon. And then this implies, well, the reciprocal. Plus 1 is less than epsilon, which is what we use here. Okay. Then we have this part here. Like, since m is some natural number of that sort, and that xn converges to infinity, we know that this part holds. So we have those two holding at the same time. And so since those two hold at the same time now, we just use the definition here. One converging to the limit means that for any epsilon greater than 0 we pick, we're going to have the difference between the limit, 1 in this case, and the term, whatever we have, be less than that epsilon. So when we rewrite that, we're going to multiply to put them on the same denominator. So we have 1 minus xn, okay? Well, negative 1 minus xn. And so this negative xn will cancel that. So we're only left with negative 1 on top. And then take the absolute value. We have 1 over xn here. This here is a bigger term than this here. So dividing by the smaller term here makes this entire thing bigger or equal because we had this here. And then, well, that by our choice of m is less than epsilon, which is really clever. I like it. Okay. Suppose an is a sequence of positive numbers converging to 0. Show that 1 over an converges to infinity. Is the converse true? The sequence converges to 0. So, what does that means? That an is a sequence of positive, so an is equal to an, pretty much. Converges to 0 means that for all epsilon greater than 0, there exists some n such that an less than epsilon is true. Okay, well, that tells us that 1 over an, by the same token, for all epsilon greater than 0, this is true as well. Okay, and set m equal to epsilon, then for all m greater than 0, there exists n such that m is strictly less than 1 over an. So 1 over an converges to infinity. Okay, I think that makes sense. And is the converse true? So what is the converse here? If this, then an converges to infinity, to 0. Is the converse true? Say 1 over an converges to infinity. Does an converges to 0? I mean, just on principle, it seems like it has to. Because else 1 on its own cannot do anything. And if an converges to anything but 0, okay, then it's just going to be converging to 1 over that fraction. Okay. Well, I guess the way you could approach it is, yes, we assume that an is a sequence of positive numbers. Okay, right? So then logically, if it's still positive there, then yes. If you relax it and then you allow an to be, well, not necessarily positive, then I guess you could have a sequence that approaches from the bottom as well. Okay? And then in this case, we'd go to negative infinity because then all the terms are negative. If an doesn't converge at all, we wouldn't be converging to positive infinity. Because, wait. Yeah, because like saying that it diverges to infinity means that every term beyond a certain point are greater than whatever bound you put. Okay? But that also implies that. Oh, okay, well, the first 90 minutes sprint is over. So let me just finish that explanation and then I'm gonna go take a break. But can we have something crazy like that? Okay? Well, if we do that, like if it zigzags like that, then at any point we pick, we're gonna have like we can like place, let's say, the boundary here, and then, well, this doesn't work by the definition. Like it's still converging towards infinity, and like we can imagine that at some point it's gonna go above, but it needs to stay above a given line. So it still needs to converge to infinity, the entire sequence. What am I saying? Right now we're talking about an itself. Does an converge to 0? Well, if an converges to infinity, this is 0. This is gonna be 0 because we're just gonna be dividing by bigger and bigger numbers. If we converge to any actual number, then this thing will just converge to the fraction. Okay. So yet again, it wouldn't be that. If we diverge because we just alternate between two values, then the entire thing wouldn't converge at all. So we wouldn't have a converge to infinity thing. Okay? We wouldn't have a converge to infinity thing. Okay? And so, yeah, the only thing left is converging to 0. And then if converging to 0, there's a few ways to do that. We could do it from the top, from the bottom. We could do it as like an alternating sequence. Okay? In which case, the terms of the sequence an are not necessarily strictly positive. Are strictly positive. I'm thinking from the wrong direction though. That's the issue, because like, if this happens, the only way for this to happen is for the term an to be, after a given point, strictly positive. They have to. Okay? Because if we have something like, well, all of a sudden, all of the work we did before that, like let's say we put our m here, well, this is no longer a good point. So we need to, like, the only way for us to actually be converging to infinity is for an after a certain point to be just like straight increasing, kind of. Okay? Or at least if not straight increasing. Does that make sense? Is there... I might be talking out my ass right now. But it makes sense in my head. I think the converse holds. So then how would you show that? How would you show that? Suppose an is a sequence of positive numbers converging to 0. Show that the limit is a converse true. The converse is this, then that. Well, yes, no? Because just take this, that's what it means for something to converge to 0. Then for all, okay, let's just write the definition. Okay? For all m greater than 0, there exists n such that n greater than or equal to that n gives 1 over an, which is bigger than m. Okay? For everything else. Well, that is only true if 1 over m is less than an. Like if this holds. Okay? For everything. Okay? For everything. Okay? But m is meant to be a really big positive, a big natural number. And so that's a really small number. And if this is true, and an here, I guess the only thing left is, well, no, m is positive. M is greater than 0. Okay? Oh, well, that's a way to use a definition. Nice. Okay, so if we have that, then an here is positive as well. And so we have that an here, well, this is also the same thing as saying that 1 over m is less than, well, an, pretty much. Absolute value of an. Okay? And so for any m that we pick, we can always find that. And then, well, we can rewrite that as an minus, like, less than epsilon, where epsilon is yes. The way to tie everything back is we have this, right? Then say for all epsilon greater than 0, there exists a m such that this is true. Okay? And so since there exists an m such that this is true, then we have absolute value of an less than absolute value of 1 over... Wait. We're almost there. Okay? We're almost there. What we want is both of them at the same time. Because this is the one we have control over. Okay? 1 over m. But we have the Archimedean property that tells us that for any 1 over m we pick, for any real number we pick, we can always find some natural number such that this holds, right? Always. Okay? And m here tells us that for any m we pick, we can always, there's always some n such that this is true. So all we need now is to find a e, pick a e, find some m such that this holds, right? And then we have some m such that this holds. Then there's going to be some n such that this part here holds, which implies that this part here holds. And then that implies that that part here holds. And therefore, now we have an converges to 0, because we can put like an minus 0 here. And boom, we're done. Nice. I think I'm pretty happy with how those demonstrations came out. So now we're gonna go to, well, how many questions we have left? 216. Damn! Yo, I'm so happy. Wow, I'm actually pretty proud. Okay, so I'm gonna go take a 15-minute break, just lay on the bed behind there and do nothing for 15 minutes. And then, yeah, I'll be right back. Like for you guys, it'll be like barely a second. So, cheers. Okay, so we return after, well, I just took a 15 minutes nap there. My brain is now hopefully awake again and ready to go. So. Let's look at the final two problems. Yet again, I put 90 minutes, similarly to last time, since we already did like all the questions for this, well, deck pretty much. The way I'll do is that I won't go for the full 90 minutes if I'm able to finish it in the next 90 minutes. Um, like before that. Everything before that is like actually like bonus. And considering the fact that I actually have somewhere to be at 6, I might even like right now is like 5-8. Okay, so considering the fact that I have something to do at 6, I might even end it earlier. But okay, so an is bounded. Okay, an as a whole, like an being bounded is like it's an example of like abusing definition, I think, because an technically a sequence cannot be bounded, a set is bounded, but anyways, it's fine. So an is bounded means that there is a L and there's a U, okay, so that any element of the sequence is at least as big as L, but no greater than U. Okay, then a and over n converges. Well, that's fairly natural. That's fairly natural because look here. Yeah, we can show that really easily using squeeze. Okay. Okay. Lim of L, like I didn't even look at anything, but it just like makes perfect sense to do that. We can use squeeze to show that. Okay. A n over n and lim of u over n. And the trick here is that, well, L and U are constants, and this goes to infinity, this goes to infinity. So the limit of this will be 0, the limit of this will be 0, and then by squeeze, this has to be 0 as well. Okay, so it's not only it converges to 0, or at least, yeah, that's how, yeah, let me see. Yeah, this makes sense. It converges to 0. So, now, I guess that we need to show why, we need to show that this is true. So, let k be a constant. Okay. In R. Then k n to infinity converges to 0. If we're able to show that, then we are done with the proof. So, how do we do that? Well, k over n is some constant, and converging to 0 means that k over n is less than epsilon for some n greater than 0 at this point. In this video, I hope that you know that. Okay. And so, what can we do? We don't know for sure about k. Okay, k, we said it's a real number, so we don't know if it's positive or negative. So what one thing we could do is this here, k over n less than epsilon. Okay, and then we can send epsilon over here like this. And like this. And yeah, I think that's pretty much it, no? So as long as we have n of this form, because like this will be k over epsilon. If we have n of this form, then any n greater than that will work. So now let's just write a proper proof. Okay. For all epsilon greater than 0, let n be defined as what? Well, we want it defined as k over epsilon. We'll take the absolute value of that, since we don't know if k is positive or not. And then what will we do? Let's say we do +1, and we'll take the ceiling, okay, so that we know it's an integer. Technically, I don't need to do all that. And for all n greater than n, we have k over n will be less than or, well, we said strictly greater, so we will have a strict inequality here. K less than n, which is going to be equal to what? It's going to be equal to k, that weird term we defined here, k over epsilon plus 1. Then I can drop the full k here. Dang it. I can drop that. Okay, the ceiling and the +1. Okay, so now I have absolute value of k over epsilon. Okay, I have that. So I can express that as what? K times epsilon over absolute value of k. Okay. Well, k technically could be negative, right? Okay. So what's for sure is that since k here could be negative and epsilon is strictly greater than 0, okay, all of this is less than or equal to epsilon. Okay? It's less than or equal to epsilon. Because if k is positive, greater than 0, then k over absolute value of k is equal to 1, and then we just have exactly epsilon. Else we have negative epsilon, okay? And then all that sequence here is less than negative epsilon, but epsilon is positive, so we also have what we need. Okay? And so we have strict inequality for any kn. I'm fairly sure that this works. Yes, this is less than that, this is less than that, this is less than that. And in this case, less than that would mean like we have, like, let's say we have our line here, we have 0 if k is negative, and n is smaller here. Oh wait, technically if k is negative, then kn being less means that we are actually moving that way, aren't we? And epsilon is over here. Yeah, I need my absolute values. Whoops. That's what's missing. I need my absolute values. Yeah, else all of what I did doesn't really make sense, does it? And then now I can do this, and then now it's just now it's clearer. Yeah, it's a good thing I sketched it out here, because technically this doesn't make any sense if I don't have the absolute values. I need the absolute values there. And boom, now we showed that. And so we converge to 0. So that's, since for any constant k this holds, and we have two constants here, then they both converge to 0, and then the middle one is forced to converge to 0. Would there be another way to show that? Well, probably. In math, there's really only one way to do things. But I think my way is good enough, so I won't bother. Use the fact, well, at least I won't bother right now. Use the fact that, oh, hell no. Oh, binomial theorem, hell no. Yo, oh, what the hell? Did we even, I don't even think we saw the binomial theorem this term. Ugh. Use the fact that n is equal to that Really? I didn't know that. And the fact that to prove that n. Oh, that looks disgusting. Oh. I mean, the binomial theorem is the like a plus b to the k thing is equal to a to the k plus okay, so I'm gonna have a I'm trying to remember now because it's been a while since I used that. So it's gonna be k. We start at 0. There's only one way to choose 0, which is why the coefficient is 0. Then I have one that is a to the k, and I have the other that is b to the k minus k, which gives 0 as well. No, I think the other one is to b to the whatever that term is. So now the second term is k to the 1. I'm going to have a k minus 1, and I'm going to have b to the 1. And I keep going, and at some point I'm going to have k to the k, and there's only one way to pick all of them. A to the k minus k will give me a to the 0, which is really just 1. And I'm going to have b to the k here, and then I have the form that I'm expecting. Okay, let me save that. And so, using the binomial theorem tells me that I'm going to have n. Well, the one we're always going to have, the only thing that's going to contribute anything is that n here, because it's just 1 on that side. Okay, so I don't really need to worry about the 1. And so I'm going to have, okay, so n is equal to that, apparently. And the binomial theorem, so I guess they want me to expand that somehow. And then I want to show that, well, all of that is less than, is greater than or equal to that. Well, the simplest way to go about that is, well, the first way that comes to mind is, in this case, when we do the expansion here, we see that n squared would happen to be, well, it would be this term here, like the term that appears just after that. Okay. The 1 doesn't do anything, so we don't really need to consider the a's. And so then we have k. We have n minus 1 over 2. Oh wait, it's the choose. Yes, it's the choose formula. So n choose 2 would be n times n minus, isn't that just that? No, n choose 2 is n times n. Wait. It's n minus 2. Wait. ACB, let's say, will be a factorial over a minus b factorial over b factorial, I think. Let me, I'll double check here, but I'm almost sure that it's that. Formula for a, if I'm correct there, then actually the problem is really not that difficult, because all you need to notice is that all the terms in the sequence here will be positive, because there's going to be some positive term. Wait, would there be some positive term? Wait, actually I'm not too sure. This might be negative. Is it ever negative? Oh frick, okay. I just need a formula. Give me the formula. Yes, okay, that's the right formula. Okay, so yeah, my memory is not failing me, so that's good. Well, what's happening here is that we're saying that this here is a term of the sequence, and then everything else. Okay, so that's a specific term of this sum here. Okay, and then all the other terms are there as well. So really, all we need to show is that all the other terms are positive. That's really all we need to show. And so now, can we do that? Well, for square root of n minus 1, well, okay, let's just think. Square root of n to the n, if n is 1, then it's just gonna give me a 0. Okay, and so we have 0. We're just gonna get 0. Okay, and so we get 0 is less than or equal to 1, which is true. If we have 2, then we have square root of 2, which is more than 1, minus 1 squared. It's going to be a positive number. And I'm fairly certain that everything else will be a positive number as well. Okay. Wait, actually it might not be. Like the... Yeah, no, actually it would be, because we always only go as high as the number itself. So, really, like square root of 2 would be positive. And then all we need to show is that if this here, okay, is always at least 1, then we're good. Okay, that's all we need to show. Now, how do we show that? Well, let's say we assume that. Then if we take both sides to the n, now we have n is less than or equal to 1, which is true. And so I guess now we can just write it in reverse, so it's true. So we just start from that tautology that n is always less than or equal to n. And then, well, you just take the power of both sides and you get what we want. So, yes, that's all we need. Since this is always true, this is a term, everything else is positive. Right now, I'm not writing it out because, like, wait, it's the last question. Oh my. Wow, that's done way quicker than I thought. Oh wait, no, actually, wait, calm down. We have this. Calm down, chill. Okay, but yeah, for this point, all we need is what we already have on the board right now. Okay, we know that this here is always at least 1. Okay, so this here is always going to be at least, like, always 0 or positive. For n equal to 1, we have this here being 0, and so we have 1 is less than or equal to 0, which is true. For everything else, I could show it by induction, I guess, but I won't bother to do it because, well, it's, I think, self-evident that, like, it's pretty self-evident that here, if I put n, like, greater n's here, and I take a single term, this here is gonna be in the equation for the summation of n using the binomial theorem, but all the other terms are positive as well, right? So it's always gonna be at least, like, for everything beyond, like, it's always gonna be true, pretty much. That's what I'm saying. Okay. And yeah, the crux was just showing that part here. Now that we know that, did we even need that? I'm not. Oh, wait, maybe they wanted us to show that because then we can simplify this. Like, if n is less than or equal to that. No, I don't think that's okay. Well, let's just go n square root of n minus 1. Right now, at this point, I'm just not stating the definition anymore because you should know it. and more like I'm just almost done here, so I'm just gonna speed run. Okay, so that's what we claim is true, and we hope that we'll be able to show it. Considering the fact that they asked us to show that, I imagine it's gonna come like play a role at some point, but I'm not sure I see it right now. Oh, wait, no, I do see it. Yes, I do see it. Okay, so wait. Does it even help me? Because if I plug the n here into that, it cancels the n outside, and I'm gonna have 1 plus this inside. Then the 1 is gonna cancel out, but then I'm just left with n square root of n minus 1, which doesn't help. Yeah, no, it doesn't really help to do that, does it? Okay, so let's just do negative epsilon plus 1. We'll do 1 this here. We're rewriting the equation to see if we get anything more interesting. No, wait. The goal is to solve in terms of n. Okay. So the first thing to do here, we already kind of like we can be. The first thing to do here is realize that, well, n square root of n minus 1 is already positive, so we can drop the absolute value. Okay. Then we can show how. Oh, maybe that's why we wanted that. Maybe, I don't know. Then I guess, can I just do 1 plus that minus 1 is less than epsilon plus 1. At this point I'm not really sure what I'm doing, but I'm just trying stuff. If I take the power of n of that and power of n of that, then I get n on this side, which is nice. Now I solved n for n, and now I have epsilon plus 1 over n. And I think that actually that's all I need. Yeah. So now I just set n equal to that thing here. And so now if we write a proper proof, okay, we didn't, I don't think we needed the fact in the middle then. Yeah, I'm erasing the rest of the stuff here. Well, technically we want n to be, this is very likely not going to be positive, so let me just take this a natural number. So let me take the ceiling of that and then add plus 1. For all epsilon greater than 0, we're jumping the gun here. We claim this. I'm not going to rewrite it. We claim this. For all epsilon greater than 0, I don't even need to write that, honestly. Well, no, I might as well. Yes. For all epsilon greater than 0, let n equal, like be defined as the ceiling of epsilon plus 1 to the n plus 1 here. Okay. Then what do I do with that? Well, for all n's greater than n, okay, we have that if, wait, no, it doesn't really work for that kind. Or does it? Well, logically, if what I do know logically, well, frick, maybe it doesn't work, because right now I have n. No, I think I did the right thing. So now I just need to like, how does that play into the whole thing? Yeah, I guess I can just like unfold it, pretty much, no? Yeah, I guess I can just unfold it. So, if wait, if n is greater than, I'm gonna have n on this side, which is not what I want. Yeah, this is not what I want in this context. Oh frick. Oh, I was so happy it was going well. What's happening now? It's really weird to see your face on like your screen like that. So, for all n greater than n, we have a definition of n. I just need to find the proper way to write this so that it works. Well, if I do n, okay, 2 to the 2, square root of 2, is square root of 2 bigger or less than cubic root of 3? Yeah, I think, yeah. Square root of 2 versus cubic root of 3. Yeah, clearly. Wait, no, it's not a clearly. But I think as a general rule, if I take a smaller number, oh wait, it's actually surprisingly, wait, square root of, why is it so close to square root of 2? What the fuck? Okay, but it's bigger. So as a general rule, well, I don't know, I don't have enough to have a rule at this point, but n, square root of n is bigger than this in our context, which is not really helpful, I think. For all a n greater than, well, no, I guess I just need to, okay. You have n like that. Okay. What's gonna happen is that we're gonna have square root of n like that less than square root of n. Okay? But here I can define simpler as that being, it's not helpful at all. Wait, how do I approach that? Frick. Okay, so here there's something that I'm missing. There has to be something I'm missing. Here, I think this is correct. This, if this is true, then this is true. Then this here is, I'm just adding 1 and then taking the n of that, using that identity. So now I have n on one side, less than that. And then if I define, yeah, but typically for those kind of problems, then we have, yeah, it doesn't work because usually the inequality looks the other way. I'm pretty sure. Let me look at my other examples. Do I have one where I actually worked it out? Okay, is there one when where did I define n properly? Yeah, here for example. Okay. Here I defined n to be what? K over n. Oh wait, no. That's what I did here. Where did I find the K? Yeah, usually I get n on this side. Guess what happens? We get something in terms of e less than n. But right now, I have something in terms of e that is greater than n, which is not nice. Well, shooting for final boss. Frick. Okay. So, this is correct, I think. Just not really helpful in this context. Okay, so let's clean this up. Okay, move it to the side and start anew. So, what else can we do? Well, the starting idea is the same. We want this here, absolute value of that, less than epsilon. That's what we want to show. How can we use what we showed here? Well, if that is true, well, what else do we have? It means that n, let's call that delta because I don't want to rewrite that, n to the delta is greater than n over n minus 1 delta over 2. And that's not really helpful because I need n's to be on one side and I need epsilon to be on another side. So, yeah, my intuition right now is telling me that I need to do something with this. Well, it's not intuition, it's just having a brain, I guess. Well, maybe it's like a total red herring, but typically for these kind of problems, if you're asked to show something, then you probably should use it somewhere. But I don't really see at all how I should use that fact, though. So it's annoying. Well, if we have that, we also have n minus 1, because we already showed that earlier. That n, the square root of n, cannot be. This is strictly positive, so we don't need the absolute value strictly. And now my goal is to solve for that in terms of n. So, well, I can just do n e plus 1, I guess. Just e plus 1. Okay. Is that the same? Yeah, it's the same. It's the same thing. Lol. Well, okay, I got to the same result, so I don't even need that line strictly. Well, I do need it, kind of, but um, yeah, I did need it for this part. So now n equal is less than epsilon plus 1 to the n, which makes sense, but I want to make dollars. um, let's see. Shit. I'm not. Okay. So, right now, epsilon plus 1 to the n. Oh, that's the issue. I have n on both sides. Yeah, that's kind of silly. Um, yeah, that's an issue. But maybe I can use that fact now. So I don't know. Let's do. I don't know what it's gonna do for us, but might as well just plug it in and see what happens. Okay. So now we're gonna be working using these here, and the goal is to make it so that, well, we have ends on only one side. So, well, what we could do to start with is, if I take the square root of n with respect to all of this, because like that's the only way to cancel that n term here. Now I'm gonna have a messy thing on this side. Okay, I'm gonna have square root of n minus 1, 2, n minus 1 here, and that is less than epsilon plus 1. Okay. Well, this becomes like I can distribute the square root on this, and this, but well, it's not square root, it's and fruit, so it's not really useful. But then, could I do something? If I make this go, okay, so I have my end fruit here of 2. I'm not too sure how I'm gonna approach that, quite honestly. N minus 1, and then I have n minus 1 like this. And I have epsilon plus 1. I can slightly simplify that side by just sending that to the other side, so now I have n. This side doesn't really change. N minus 1. And minus 1 in terms of with the n fruit of 2 here times epsilon plus 1. Okay, so now that we have that, what can we do? This I can treat as one term maybe, and bringing it inside, and then I would have this minus this, and hopefully some magic will happen that will allow me to solve it. So at this point, I'm gonna treat this as like a delta that we had earlier. So I'm gonna have n square root, and I'm just gonna work on this side to see if I can do something. I'm gonna have the nth fruit of n minus 1, okay, minus, well, all the same thing, n minus 1, okay. Now, what can we do? We can do n negative n squared minus n on this side, plus n on this side. On this side, I'm gonna have n squared minus n, and then I'm gonna have, well, 1 over n here is what we're having. Right? I have 1 over n. So if I add that, it's gonna be, sorry. I'm not sure it's helping much though. But I'm gonna have just taking n squared. It's n squared minus n, and then I still have the n to the n here. And so I guess I can factor that out. Did I really? Yeah, no, I just that's not funny, because now I'm just back to that, so I don't really want to factor it out. What can I do? If I do that, I would get 2 plus 1 over n. So I would do 2n plus 1 over n. So I'd have 2n plus 1 over n, and then n plus 1 over n. So n to the 2n plus 1, and then I put that over n. I'm gonna have minus, n plus 1 over n, minus n to the n plus 1 over n, minus n. It's not getting simpler. It's not getting simpler at all. Okay, that is less than, and even, okay, no, that's a doozy. Yeah, we have the over n on that side as well. Yeah, so I can't even send it that way. I need to keep it here. So I'm gonna remove that, put a 2 here, and now we have the same equation. Okay, so all the n's are on one side. But what can I do with all these n's? Maybe abandon and try something else. Yeah, I think that's the best way to go at this point, because this here cannot really be simplified, can it? I don't see an obvious way to simplify it, that's for sure. Well, one that is not what we had already here. How can I simplify that? Okay. The goal of an epsilon proof is to show that this here, okay, this here is less than epsilon. So I guess I can use the approach I used earlier and keep bounding like, okay, n square root of n minus 1. The issue with that is that for that to make sense, I need the epsilon there. I need a 1 there, so I can't just do it, whatever I want. Okay, so epsilon here. This is equivalent to saying that epsilon 1 minus that. And then can I do something with this here? Epsilon plus 1. I don't have anything that jumps to my mind, quite honestly. Or maybe this. Now that I don't have the one on the over there, if I bring the 1, yeah, no, I'm just gonna cancel that one with that one. Then I'm gonna have square root of n to the n, so that's cancelled, and I'm just, yeah, so it doesn't really help. If I take everything to the n, 1 minus epsilon to the n, and then I have epsilon plus 1 to the n. It doesn't help because we have terms in terms of n on both sides, so that's quite a pickle. How do I show that? Yep. Yeah, I don't know how to approach that. Okay, maybe the example they gave above was to tell us how we should do that. Well, it's quite different. Oh, that's a tough one. Okay. Wait. Why is the limit equal to 1? Let's say I take 10,000. I take 1,000 here to the 1 over. It's gonna be close to 1? Oh, yes, it is quite close to 1. Then why is 3? Is like 3 an exception then? Yeah, because like that here is bigger than 2. Yeah. When does that become true? Like imagine that 10, yeah, that is less. Huh. So, in fact, we do have something. Or do we? Because since we have this and we know that And at some point, is that even useful? I don't think so. Yeah, there's no way that. Oh. Yeah, no, because like what I want here is just n itself, because then I can cancel the thing. But then if I take a smaller n, yep, that doesn't work. Frick. Yep, I'm not seeing it. So let's just, I guess, talk through it. Like, I'm talking as if people were listening right now, but how many people are crazy enough to tune in and like watch a video in like 2:30 minutes, 2 hour 30 of some dude solving real analysis problems? Like, if you're there, you're a G for real. Or you are a G at, I guess, if you're a girl. I don't know. How would I do that? Because we know what the definition of a limit is, so it's not an issue of definition. The absolute value can be expressed as we did earlier, but it doesn't seem to help much. We can show that n, if I take 1 over, is there some magic that happens that makes it work somehow? No, I don't think there is. Oh, I don't see it. Sheesh. Okay, at this point I'll see if I can find like a hint or something. And fruit of n as limit 1. Cora for the win, maybe. Evaluate the limit. The constant way to prove this is using inaccurately L'Hopital's rule. No, I need real analysis here. You want L equal to... Yes, you can do this by taking the natural log on both sides to bring the power down. Wait, I can? Real analysis. I need the real analysis. Real analysis. Okay, there's videos about this, so it's not an easy problem. At least that's good. I'm trying to understand, or maybe it's an easy problem. Maybe, never mind. I'm trying to understand a proof, and I'm a beginner. Proof that converges to 1 in case that that's not what I'm looking for. Yes, limit of the n fruit of n. Okay. We had the proof using the binomial theorem. You have obtained using the binomial theorem that since n is n minus 1 greater than minus 2, then we have an. Wait, let's look at that. I'll take a screenshot of this so that you can. Right now, we'll copy the answer by Jamie Kamsky. Thank you very much, Jamie Kamsky. and try to understand what it is. Okay. So, with binomial theorem, since n is greater than or equal to 2, we have n minus 1 is greater than n over 2. Yeah, sure. A to the n is, let's see, this is quite similar to what we had. Is it? No, it's not. Wait. Where is u? Here. Yeah, it's kind of similar. It is kind of similar. We have the n minus 1, 2 thing. The only thing that changes is that they have a instead of n. But yeah, I guess it doesn't have to be a. It can be for general n. Wait, a to the n? Yeah, I guess that works, because if you take this, does it work? You're gonna at some point. Wait, the inequality is it's pretty different. How did, like, the way how we got ours makes sense, but how did they get theirs? Substituting a to be square root of n, then you get, okay, then you get n square root of 2 over 2. Yeah, no, I'm not gonna front. I'm not catching it. So this is the inequality we have. This is the inequality we have, and then n squared minus 2n minus n. Okay, well, I guess that's where it ends for today. I'll asterisk this one. It was quite a hard one. So yeah, we'll come back to this. No, I probably won't come back to this on video, but I'll look for an explanation for that. So if you watched all of that, thank you very much. And that's it for today. Peace.